there. All right? So from this particular crossing right here, I'll put a dot. From that particular crossing, I get the relations, what? B plus C equals to A plus T. Okay, from this crossing right there. What if we look at this crossing? What relations do we get right here? So we get D plus E.
Would you say A and F?
Yep. Right? And then from this one,
CFD.
let's see here. Oh, is it D plus C?
Okay, and then E and F.
D plus F. So I got this one, this one, this one. I guess I've also got this crossing up here, right?
Yeah.
So A plus B, C plus, you gotta use your imagination, F's all everywhere.
Yeah.
So let's see, there's 1, 2, 3, 4. I think there's just 4 crossings, so we get 4 relations, right? How many regions are there? 6. So our relations matrix to describe the Alexander group, you know, if we put A, B, C, D, E, F as the order, right? We get, so I'll start with this one, yeah? 1, 1, minus 1, minus 1, 0, 0 for the first one. 1, 1, minus 1, minus 1, 0 for the second one. 0 A's, no B's. 1 for D, 1 for C. I mean, you see there's ambiguity, which one you put 1 minus 1, you know.
Yeah.
I'm just, I don't know how I chose, I don't even remember what I did, honestly. I made a decision, and I gotta write this down, but anyway, there it is. So the Alexander group of a knot is an abelian group, which will be an invariant of equivalent knots.
Yeah. Do your minuses mean anything? Because I see that like you kept all their left side positive, but except the first one, like the first
Doesn't, it just means I chose to make A positive whenever I saw it.
Oh, okay.
That's all it means.
Okay.
It doesn't mean anything. And then, you know, you could write down A, B, C, D, E, F for the mirror.
Yeah.
And you could write down its relations matrix. And I believe that you can show that they have the same Alexander group.
Yeah, by showing that you can set it up in 0, 0, A1 through A4.
Right, so we could reduce that matrix using rows and column operations to see what we got. Which I believe is one of your homeworks.
Oh.
I think your homework, I might have given you like the, what was it? I think the answer to your homework is probably in this PDF, by the way. Not to ruin it for you, but I'm trying to remember here. Yeah, I think I said to, let's see, here's that one. 1, 1, 0, 0. I think this is the same one as example 23, and it turns out, I should mention something, that this works out to like, I think this is equivalent to zero, one, one. Is it zero? No, where's it? Goodness gracious. Well, there's a 5 down here, I believe. I mean, supposedly it's isomorphic to z cross z cross z5. I'm trying to remember what that means for the matrix. I think
Now, earlier you said if you have a row of zeros, you cross by another thing of z. And here I see you only cross twice by z.
yeah, I think I need 2 rows of zeros. But I think I'm trying to say is what would a 1 here mean?
Yeah.
Okay, so this if this went to that, right, that would mean z cross z mod 1 cross z 5, and see this
It's just z.
is 0
Oh.
because 1 is z and z mod z is isomorphic to 0.
Yeah.
So in this game, when you get a 1,
Mm-hmm.
what does 1 mean? That means that you can relabel the relations and the generators such that in the relabeled system, the third generator is equal to 0.
Yeah.
1 times the generator is equal to 0. So you don't need it.
Yeah.
It's irrelevant, right? Like you could always take anything you have and adjoin additional generators that are just set to 0.
Yeah.
Right. So conversely, if you work out simplifying your group and you get to the point of one of the generators just being equal to 0,
Mm-hmm.
you can remove it. And that's why we started with, well, what did we start with, actually? I mean, I'm not even doing it justice, right? Because it's got 1, 2, 3, 4, 5, 6.
Yeah.
So it doesn't, it's not this either, right? This isn't what we get. We get,
I mean, it's 4 rows. Oh, yes, what you're saying. Yeah, you got 6.
let's say this, man, I don't know what the, I'm can't see it right off the top of my head, what the matrix would actually reduce to. But anyway, there's something for you to sort through in the homework. I hope that makes sense. Anyway, definitely the row operations and column operations make sense, right?
Mm-hmm.
Okay.
Does that mean something in linear too? Like when you can do both, like the row, is that what you call the Smith form?
Yes, let's talk about that. Oh. Huh. Well. Huh. Oh. Hmm. Hmm. Well, I think what we should be able to get to is 1, 1, 1, 5, and then zeros. Everything else is zeros. But if you look at this PDF, he describes how to throw away, like you don't have to keep writing everything if you think through it correctly, right? Like once you get a row of zeros, you can dispense with that, you know? You don't really want to throw away a 1 though, because that tells you that that generator's relevant. So like this,
So where do you get the extra copies of Z from?
these two.
Okay.
So, yeah, essentially you can just chop off the part with ones and just focus on this. This is all that matters.
Yeah.
You've got 5 times 1 of the generators is, you know, one of the factors. That's 0, that's Z5. And then this and this gives you the Z and the Z. Whereas these three basically says that in the relabeled one, A, B, and C are all identically equal to 0, so you don't need them. So I think this is, you can get to that, but the current solution I have, I got this pesky -1, and anyway, I made a mistake in my solution that I have sitting here. All right, so I'm trying to gather all this stuff together so I don't get it mixed up, because I do not have a stapler here. So next up, we will talk about the Smith normal form calculations for the for like a matrix. Okay. I'm gonna hit the stop button here. Oh man, that's annoying.